So in this question, we're asked to find the value of k, which is the transfer function for the controller, if the system is to have a settling time of 10 seconds. We're allowed to assume that we have second order dominance, but we're asked if that assumption is actually valid. So the first step in going through this is going to be to find the overall transfer function of our system, which is essentially C on R. Once we've got that, we should be able to look at the characteristic equation and the time response properties that we can draw from that. So let's go ahead and go through that process to start off with. So we're going to need the transfer function of what's on the top line here. I'm going to call that the open transfer function, remembering that open is when you're not considering the feedback loop, so it's just the forward part of your system. So it's just going to be the transfer function of the two blocks multiplied together. We've given the plant one over here. So multiplying these together, we're going to get 12k on 2s cubed, 12s squared, 16s, and 2. So now what we need is the feedback transfer function. So that's the transfer function in here. And because it's just drawn as a line, what we can assume is that this is exactly the same as unity feedback, or it is unity feedback, and that means that the transfer function is equal to 1. So whatever is here is directly fed back into our summing junction. So now we need to find the overall transfer function, same as the closed transfer function. Alright, C divided by R. So we know the general form for a negative feedback loop looks like this, where this G is the open transfer function G. So all we need to do is go ahead and substitute in. Divided by and this gets multiplied by 1, which is H. Alright, so what we're going to find with the transfer function here when we cancel it down is all that we're ever left with is going to be the open transfer function with the addition of whatever's on the numerator appearing down on the denominator as well, being added on. Alright, this only works when you have unity feedback, where H is equal to 1. So I'm going to go through this process, but what I would expect is that this is going to end up equaling this. Oopsie, that should be a squared. Okay, so you can shortcut it in the future for unity feedback. We end up with the open transfer function with whatever's on the numerator ending up on the denominator as well. So let's go through and actually prove it. So the top line is going to remain the same. Okay. For the bottom line, what I want to do is make sure I have the same denominator for both terms. So that's going to mean I need to multiply this 1 by this on this. Oops. Alright, so these top and bottom line cancel out, so all you're left with is the 1. And then I still have over here, I've got 12k times 1, which is essentially 12k, divided by that same bottom line, so I can just add this into the fraction. These end up cancelling with each other because they're the same now, and we're left with what I said we would be. So in the future, if you want to shortcut it, whenever you have unity feedback, it's always going to look like this. And just to show you, yeah, exactly the same as what I predicted up here. Now look at the characteristic equation. So remember that that's the bottom line of our transfer function, except that we need to make sure that the highest power of S has a 1 in front of it. So at the moment, our highest power of S has a 2, so we need to divide everything here by 2, top and bottom lines. So if we divide this by 2, it's just going to be 6k, and if we divide this all by 2, oops, sorry, 1, we end up with this, So this bottom line here is our characteristic equation, and we can equate that to the third order version of a time response characteristic equation. Remembering that if we're assuming second order dominance, that's going to mean that we have a second order part to our transfer function, which looks like this, and a first order part, which looks like this. And we're going to assume that this part is dominant. And we're going to assess the quality of that assumption at the end. So what we need to do is expand out this right-hand side of our equation, and I did that in the time response video. So let me go through and write out the nicely expanded version where all of the powers of s are factorized. Okay, so that's what we end up with. We've got a cubed, a squared, a constant s, and just a random constant on the end as well. And we can go through and start equating together the constants in front of each of our powers of s. Now, in order to be able to do this, we do need one extra piece of information, because if you count up the number of variables and the number of equations we have, there's actually too many. So we get this extra piece of information from the criteria that we need to meet, and we've got the criteria is a settling time of 10 seconds is what we're aiming for. So we can turn this into something to fit our equation. Remember that we have this equation for settling time where it's equal to 4 divided by omega n zeta when we're assuming that the second order part is dominant. I should just make a note of as well at this stage. This is an approximation equation. Okay, so it's not exact. So when we go to simulate this, we wouldn't expect to have it perfect. So if we know that we've got a 10-second settling time, we can sub that in. And if we rearrange, we can find that omega n zeta has to be equal to 4 divided by 10, which is 0.4. So that's the kind of extra equation we have to be able to complete our set of simultaneous equations. So if we pop down here, where we're up to, we know this extra piece of information. Alright, so let's go ahead and start equating things together. So the s cubes have to equal each other, and we have 1s cubed equals 1s cubed, which is true, but not going to give us anything to solve our question. So let's move on to the next one, which is the squared part. So we've got the 6 in front of here has to equal this expression here. Alright, so we're able to substitute in this one here from our criteria that we need to meet. And plus p. And that means that we're actually able to solve for p quite easily, and it comes out to be 5.2. Alright, so that's one thing that we've got. Remember, we're aiming for k here. So if we go to the next one, which is the s terms, we can equate those together. And we can sub some stuff in. So we've got 8, omega n squared, we don't know omega n yet. We know these two multiplied together though are equal to 0.4. And we've just solved for p. So actually the only unknown in this equation is omega n, and it comes out to 1.96, and this is a angular velocity, so it's going to be in radians per second. Alright, so that's good. So now we can go ahead to the constant term, so 1 plus 6k has to be equal to p omega n squared. Alright, so rearranging for k, we're going to get this, and we should be able to sub in because we know all these things. So 5.2, 1.96, we end up with a k value of 3.161. So that's the answer that we were looking for. So assuming second order dominance, if we set k to be equal to this value within our system, back up here, what we would expect is that we have a settling time of 10 seconds for the system. So now what I want to go and do is double check whether my assumption for second order dominance was actually valid. Because if not, then what we've just calculated is not going to be correct. So coming back down, to check my second order dominance, what I need to do is find the poles of my transfer function, or my characteristic equation, I should say more specifically. So what we need to do is find out where our equation here goes to 0, what values of s cause that. So I'm actually going to go back and take this version of our equation, and I'm going to substitute some values in. So we worked out omega n times zeta had to be 0.4, and we worked out omega n needed to be 1.96 just here. We also found p, it was 5.2. So if I simplify this, 1.96 squared is actually 3.84. Alright, so we just need to figure out what values cause our equation to go to 0, values of s. Okay, so it's going to happen when s is equal to negative 5.2. So that's going to come out of here. Okay, from this one here, if you apply the quadratic equation, or you put it in a calculator or even MATLAB, you can figure it out. And we get two poles coming out of this. They're complex conjugates. So negative 0.4 plus or minus 1.92i. So I'm going to plot these on a diagram. Oopsie, that was meant to say imaginary axis. And this is the real axis. So let's plot this one here. That's pretty easy. It's only got a real component, so that's going to sit on the real axis. And it's out at negative 5.2. And then this one has got, well, there's two of them, and they've got a real and imaginary component. So they're going to sit off the axis a bit. Okay. So the real component is 0.4, and the imaginary is the 1.92. And one is negative and one is positive. So for dominance, the further a pole sits from the imaginary axis, the least impact or the less impact it's going to have on the result. So what we have is this 5 times rule of thumb, which we can apply. If a pole is more than 5 times further from the imaginary axis than other poles, then it's going to have a negligible impact on the response. So let's assess that. So we have pole at 5.2, and these two poles have a real component of 0.4 off the axis. So if we work this out, it comes to be 13. So there's a ratio of 13 times between these two poles. Now this is greater than 5, so as a result, so therefore, second order dominance assumption is valid. So that's the answer to the second part of the question, where it asked us if this assumption was valid. So what we can conclude is that when k is equal to the value that we calculated, 3.61, we should have a settling time of about 10 seconds. So I've written myself a program to try and check that. Again, I've just set up the transfer functions in MATLAB with the gain value that I'm looking at, and I've given the step response. And this is the plot that I end up with. If you look at the system characteristics, we're interested in the settling time, and we get a value out of about 9 seconds. This is almost 10. The difference that we have is going to be partly due to the impact of that third pole. But the main thing that's going to cause our difference between the 8.92 seconds that we've simulated and the 10-second settling time that we calculated based on is due to the fact that that equation is this one here is an approximation equation. So it's not going to give us an exact solution, and I would say that 8.92 seconds is within what we'd expect for the accuracy of using this settling time equation. So that's all there is, and I'll see you in another video.